Okay, Roberto, thank you. First of all, I want to thank you and for inviting us to present some of our research here in Brazil. My name is Tiago. I teach at Federal University of São Paulo, in the city of São Paulo, and I am presenting I'm presenting these slides as well the paper that is have as the leading author Professor Bianca Vieira from the University of São Paulo. Yes, we have a couple universities at the same city. I teach geomorphology at undergrad course in geography, the Department of Geography. And my main research focus is about landslide susceptibility mapping using some of the tools that I will present here. And this theme caught my attention because Brazil, as the title says, have a recurring problem regarding mass movements all over the country, especially in one of the landforms known here as Serra do Mar, that I will show some pictures. And this issue has bring to everybody a lot of attention because of the damage that caused every year. So first, I will present to you guys some pictures of this recurring issue in Brazil, and after we'll present a brief about the paper published a few years ago that has Bianca as first author. So landslides in Brazil are happens every year. They cause a lot of loss of life, homeless, and economic losses, of course. And we have some registers, historical registers since the 20s. But since the 60s, the studies regarding steams are enlarging. It's getting more people attention, especially because the most susceptible, most prone areas to this kind of process are inhabited for a long time. It's the inhabitations in these areas are associated with the colonization process that started in the east shore and the east coast and to the hinterland of Brazil. So you can see this black and white picture from the 60s in the city of Rio de Janeiro. As you can see in the back of the buildings, a landslide that reached the urban area. Second, also in the 60s, we have some main moments in Brazil that the disasters caused by mass movements were very intense. On the 60s, 80s, and the 2009, 2010. So Serra das Araras is part of this landform compartment that faces the Atlantic Ocean. So this mountainous terrain that goes from south to the southeast Brazilian coast. So Serra das Araras is part of it. It's in the way from São Paulo to Rio de Janeiro. Next, you can see Santa Catarina. It's a southern state where the Serra do Mar, let's say, begin in the south, and especially in the Itajaí Valley. 2008 was affected severely by mass movements and debris and mud flows, and as well of floods. And then at least 140 people died. And Cubatão, that's a town, a city near São Paulo that holds one of the largest industrial plant we have, that was affected severely in 1985, as you can see the pictures. And this chart shows the number of people that were killed in these major events since the 80s until 2010. And unfortunately, we been registered in the last decade or so a number of events that cause loss of lives. And in this year, our rainy season here is our summer goes from December to February, March. So this is the rainy season. And then this chart shows this variation number of people killed. And unfortunately, as I said before, there are a lot of registered in the last decade or so, like in Petrópolis, and Petrópolis, the town of Petrópolis in Rio de Janeiro, and the town of Franco da Rocha near São Paulo, that register severe damage by mass movements and floods in this year, 2022. So as I said before, summer is our hard moment. The rain season is starting middle spring, like let's say now, late September, early October, and keep increasing until summer that starts in December. And December, January, and February are the worst months for these issues in Brazil, that we have a lot of registers of this kind of process being triggered so by the rainfall and reaching urban areas. So as I said, often during summer, Brazil is affected for widespread mass movements, events, especially shallow landslides and debris flows. Those are the main types of mass movements we have in Brazil, and the triggering factor that stands out is the rainfall, especially during summer season. This is the city of Rio de Janeiro is in the coast, but the mountainous terrain that they call Serra do Mar is in the back of the Guanabara Bay. So this is the picture after this mountainous terrain has been affected by a large number of mass movements, special shallow landslides and debris flows in 2011. And two questions comes out from observing this. One is associated to evolution of landscapes. So these landscapes evolves through mass movements. And then on the other hand, in this landscape, we have the many areas under hazard conditions because it's well populated. It's the first area that has been widespread populated since colonization times. So, as I said before, economical, social, environmental laws are very common when these mass movements are triggered. And a recent study in Brazil showed that at least or more than 8 million people living in risk areas in Brazil associated with mass movements and floods, especially shallow landslides and debris flows. And these slopes that form these landforms carry a larger volume of sediments and reach a large volume of sediments are carried to the drainage network, filling up this drainage network and building up this kind of landscape that presents steep slopes with a lot of material prone to be moved and bottom valleys that are prone to floods or to carry debris. And of course, these bottom valleys are in some place occupied by urban areas or by farmers. So the combination of this land use associated with the mass movements, but 8 million people in Brazil living under risk conditions. Serra do Mar is this landform compartment it's this mountainous compartment that face the Atlantic Ocean, as you can see here in this map. So you can one of the key characteristics of this area are steep slopes, and some of these areas get a lot of rain during all year, especially during rain season. So as I said before, the idea that this kind of landscape evolved through mass movements give us a better understanding about the genesis and the evolution, and especially the recurrence of the process. So Serra do Mar, this landform compartment, as I said before, it's very peculiar. Used to be forest all over. Of course, due to the colonization process, the forest has been diminished severely, and also rainfalls have reached high values in this compartment. So we call this landform Serra do Mar, that is because it's faced to the Atlantic Ocean. So it's a kind of a step from the Atlantic shore, lowlands of the Atlantic shore, that separates the Atlantic shore lowlands to the hinterland, that's a more plateau terrain. And we have a lot of register of mass movements that are somehow covered by this vegetation. And as you can see here in the picture, steep slopes covered with rainforest are the two main characteristics of this mountainous range that extends about 15,000 kilometers since the north Santa Catarina state, the north part of Santa Catarina state, until the southern part of Rio de Janeiro state. And you have a sort of parallel mountain range that goes a little bit, goes north. We call all this system the Mantiqueira system. But our research focus is in the Serra do Mar mountain range. Another important thing about this landform compartment that holds big cities, or holds pathways that are that have a very important, very economical importance. This region has a significant economical importance since it is crossed by railways and highways that connects the Brazilian large cities, São Paulo and Rio de Janeiro. And these highways and railways are very useful to export our commodities, our goods that are produced in the hinterland to the ports, especially the Port of Santos. Port of Santos is located in the shore, of course, and the São Paulo city is just in the back of this mountainous range here. And you can see also very important highways that cross the area, as well railways that go meandering, if I can say so, around this mountainous terrain and reach the main cities in the counter hinterland. So one of the main events that happened in Brazil, it's in the 60s, 66, 67, that were well studied. This is the city of Caraguatatuba in the shore of São Paulo state. It has been severely affected by mass movements and debris, mass movements, shallow landslides and debris flows. You guys can see here the landslide scars produced by this process, and here you can see the highway. So this process happened in the March 16, 17, in 67, were first studied by the employee in Cruz that mapped the deposits and the outreach of the deposits associated with the mass movements. In fact, if you go to the Caraguatatuba today, nowadays, and You stop at the same point of this picture. That is a sort of viewpoint in the road. You can see the landslide scar preserved by some sort of peculiar vegetation that grows in the area, that in stopping the forest to recovering. Another picture here regarding the mass movements that affect Serra do Mar mountainous terrain. And this is near the city of Cubatão. You can see here the slopes that form Serra do Mar. And exactly in this area that contains the watershed that will present you guys a little bit ahead. And this area is very important because you hold here highways that are used to transport the goods produced in the hinterland to the port of Santos. And as well, you have here some industrial plants that are very important for Brazil. And these plants are situated in the footsteps of these slopes that are very prone to mass movements. Another event that happened was in Rio de Janeiro, with more than 55 people killed in 1996 in the city of Rio de Janeiro. That were two watersheds affected by mass movements. As you can see here, debris flows with very large blocks being moved along the drainage system. And this happens one of the massifs that you can find inside the Rio de Janeiro town. Is a bit far from the Serra do Mar mountainous terrain. And here you can see the Itajaí Valley, located in Santa Catarina state. Is the southern part of Serra do Mar mountainous terrain. With a similar physiography, you can see steep slopes surrounding the bottom valleys that are used for farming. And these bottom valleys are filled with sediments. This event happened 2008 and killed you guys may have seen during the presentation the amount of rain that was recorded. This is one issue about our research here. Usually the rain gauge is not at this point, so we somehow make some estimation to understand how much rain happens during the event. But like this one, is 720 millimeters in 72 hours of rain. It's quite a lot of rain, and causing these mass movements. And here in 2011, the Serra do Mar in the state of Rio de Janeiro was severely affected in the 11th and 12th of January, 300 millimeters in 48 hours, causing widespread mass movements in these towns located in Rio de Janeiro state. It's not the Rio de Janeiro city, it's in the Rio de Janeiro state. This is a bit west of Rio de Janeiro city. And what all this occurrence, all these events that I'm been reporting you guys, made the Brazilian government create a policy that in order to prevent risk situations like those I just showed you guys. And we have a law since 2012, a year after, that require the municipalities to make susceptibility maps for the towns that are located in this kind of terrain. And we have a national center that was created in order to monitoring rainfall and risk areas for Brazil. So all these occurrences encourage the government encourage not the best word, but force the government to take actions. And this law was passed in 2012, and this center, national center, was created as well. So another example here happened also. 2010, 2011 was a year of disaster in Brazil. We have a lot of registers regarding this kind of process. Here you can see a pic of Google Earth, seeing the shore and the mountainous, this Serra do Mar mountain range, this step that separates the lowlands of the shore to the hinterland. And one of the affected cities is this one, São Luís do Paraitinga. Was affected, the town itself was affected most by floods, but the area around the town was affected by shallow landslides. So more than 500 landslides were recorded during the late December 2009 and early January 2010. And during this time, we registered at least 600 millimeters of rain. And there's some pics of the São Luís do Paraitinga, because this is a historical city in Brazil. And also there is a cultural value for the city, because in the 17th and 18th century, there was a pathway from the Minas Gerais, like the area that produces gold, the mining area in Brazil. There was this pathway that connected this mining area to the shore in order to export gold and diamond. So this path became a sort of touristic attraction, and many people used to go through this path as I said, touristic attraction. And São Luís do Paraitinga is a part of it. So besides all this damage, there is this cultural meaning about the cities that grew along this pathway, and all this historical value and the national and cultural heritage that was built on this path. São Luís do Paraitinga is one of the cities, as you can see pictures here from the 50s. And also, São Luís do Paraitinga attract a lot of people because of these folklorical parties. And the main plaza of this folk meetings is in front of the main church. And this main church was destroyed during the floods of 2009, 2010. The Paraitinga River flooded and occupied all the historical center that goes from this another church here, this street and here, and destroyed the church. This church was, it was at least 200 years old, was built not with concrete, was built with more ancient techniques, and could not handle the amount of water and collapsed. As well, you can see here the river banks collapsed. So today the church was rebuilt, and all the river bank was reinforced, the structure. But here you can, one of the clear example about our risk areas in Brazil. People living near the riverbank or occupying steep slopes prone to mass movements, and all this heritage that also occupy areas that are suitable for mass movements and floods. Here you can see what's left from the church that collapsed in 2000. It was early 2010. And another part here that was the municipal market, but the municipal market did not collapse, but all the town was underwater. And another main event that happens here in Brazil was in 2014. In the southern part of Serra do Mar, we have this, we call it Ribeira Valley. It's the valley formed by the Ribeira do Iguape River, that's one of the most preserved rainforest areas in Brazil, in southern Brazil. And in 2014, January 2014, intense rainstorms, nearly over 120 millimeters in 72 hours, triggered hundreds of landslides and debris flows that also reached the town of, especially the town named Itaoca, and destroying the town. So the mass movements happens in the upper valley, but the debris reach the bottom valley, and the water carry the blocks itself, as well the wood, the trees, and this more fine sediment, and the trees that reach the town and destroy their infrastructure, as you can see here. This bridge that is in the central part of the city hold all this wood material, and the river start to overflow its banks and reach the town. And also during the process, the wood that were carried along the river start destroying the house. 25 people were killed, and at least 300 people homeless during this episode. So, saying that, this background about mass movements in Brazil, I'm presenting here some brief aspects about the paper entitled Assessing Shallow Landslides Hazards Using the TRIGRS and SHALSTAB Models in Serra do Mar, Brazil. This paper was signed for different authors, and the leading author, as I said in the beginning of the presentation, is Professor Bianca Vieira from the University of São Paulo. So the idea about this paper was to compare the performance of two different models, two physically based models, TRIGRS and SHALSTAB. SHALSTAB is a model that has been applied in Brazil since the 90s. It's a well-known model here, different assessments, and TRIGRS is a less used model. So the idea of this paper is to compare the efficiency, and as one of the questions is which method is best. Like, there are a lot of methods in order to map susceptible areas to some sort of process, in our case, mass movement. So some methods are based on some level of understanding of the process, and you can infer a weight on some parameters. But these methods rely a lot on the experience of the researcher. So physically based mathematical models does use not to rely on the subjective experience of the researcher, and instead applies equations that describe physically relevant process, disregarding subjective opinions. So the idea was to use models that we know that are low cost, that the inputs are based on some physical parameters, and the results are based in some equations, and these somehow avoid some subjective or opinions. So these models also can be used to predict landslide susceptibility under different land use scenarios. The study area evaluated in this paper is one of the watersheds that reached the city of Cubatão, one of the pictures I showed before. So encompass 3.6 square kilometers, and in the bottom of the valley, or in this watershed, we have a large petrochemical plant built in the 59, and a large industrial park, all this located in the city of Cubatão. So Cubatão is a city that are in the Serra do Mar, and behind the Serra do Mar to west, you have São Paulo city. To the east, on the shore, you have the port of Santos. Some characteristics of the watershed. 60% of the hill slopes are between 400 to 800 meters elevation. So this is something curious. Serra do Mar varies the elevation depending on where you are. So you have in São Paulo specifically, the altitude is not as high as in Rio de Janeiro or in Paraná. So Serra do Mar reached higher altitude in other points. And 42% of this the slopes are within 30 to 40 degrees angles. So it's a quite inclined terrain. And as you can see by the numbers, are located a little bit far from the shore. So the idea was to test different scenarios using these two models. And for all these models, the main data, the main input are the digital elevation model, the digital elevation data. So one of the issues where we are working on here that are that we can choose two things when we decide to use these models, the DEM and the landslide scars, because the model, the equations behind the model are already there. So you can vary the parameters, but the equations will allow the computer to create these scenarios, and the equation does not carry any variation. So besides the DM and the landslide scars, we can test different values of inputs, and as you can see here. So 6 scenarios were tested for each model. And the main issue is the variation of soil thickness and the cohesion. So the first 3 scenarios, cohesion was used 1,000 pascals, and in another scenario 6,000. So this, and also you can see a total unit weight of soil varying a little bit, and also the soil maximum thickness from 1 to 3 meters depth. And the other values are quite the same. So the idea is which model responds best, varying this parameter if you compare the number of cells to the landslide scars. So for that, there is 356 scars were mapped from the 1985 event, what represents 3.7% of the total area of the basin, and two methods were used to compare. We call it scar concentration and landslide potential. The idea is when you compute, it doesn't matter which model is it, you present different cells. Each cell has a value. The idea is to see what cell is in the land scar perimeter and check if the landslide scar is coincident with the cell that says is unstable or stable. So the scar concentrations presents the ratio of the number of cells in each susceptibility class affected by shallow landslides to the total number of cells in the basin, and the landslide potential somehow gives us a different perspective because shows if there are a lot of cells that are unstable in the total area of the basin. In simple words, if you paint all the watershed in red and say that's unstable, we can assume easily that inside the landslide scar will be red as well. So the idea is somehow balance this evaluation from the scar concentrations to the landslide potential, being the ratio of the numbers of cells in each susceptibility class affected by the shallow landslides to the total number of the cells in the same susceptibility class. So using this model, the idea is not to say all the watershed is unstable. So it would be an easy answer. somehow the scenarios must balance stable and unstable areas. As I said before, there were a lot of landslide scars in the 1985 event. These are some pictures of the area. As you can see, the shallow landslides happens in the upper slopes, and the material reaches the drainage system, and all this flows as a debris flow to the lowlands of in the foot slopes. So one important thing to say is that SHALSTAB or TRIGRS are models used for shallow landslides, not other process. So the idea here was to verify which model fits, which scenario fits best the landslide scars, and this is another issue we've been addressing here. Which landslide scar is the ideal to validate scenarios like this? You may talk about this in another moment. So here's are the results of TRIGRS model. Look, so there's 6 scenarios: A1, A2, A3, B1, B2, B3. The main difference here is like if you increase cohesion value, it's decrease the unstable areas. TRIGRS present us a result based on the safety factor, above 1 or under 1 value. This is another key issue about comparing one model to another. How each model present the results. So in this paper, the idea was the number of class presented by SHALSTAB is different from TRIGRS. So the idea was to divide in the middle the number of class of SHALSTAB and compare with the TRIGRS. But what you guys are seeing here, that in scenarios A1, A2, and A3, few variations were identified in the spatial distribution of susceptibility class. That is, as soil depth increased from 1 meter first scenario to 2 meters, the A3 scenarios, the unstable areas experienced a 10% increase. Between 2 meters A2 and 3 meters A3, the increase only 3%. Different geotechnical and hydrological parameters in scenarios B1, B2, and B3 result in important difference increase in the percentage of stable areas in 3 scenarios. And in scenario B1, 100% of the basin was classified as stable, as you can see here. So it's all blue. And in B2, 97%, and in B3, 87%. So in group B, the 3 scenarios had higher scar concentration class stability with only a few scars. In other words, we have a lot of stable cells associated with areas already affected. So in SHALSTAB, one of the things that calls attention is the amount of red on the unconditional unstable areas in the first 3 scenarios. So like the results of the TRIGRS model, there was a strong similarity in the spatial distribution of susceptibility class for group A. The most significant change, an increase of nearly 10%, occurred between scenarios A1 and A2. And consider only the unconditional unstable class, the red one, the frequency, frequency is a parameter that was not present before, but is the distribution of the class along the watershed, has exactly the same percentage values as the unstable class of TRIGRS. In other words, TRIGRS and SHALSTAB TRIGRS present the same amount of unstable areas, lower than 1, as SHALSTAB present as the unconditionally unstable area. As I said before, the SHALSTAB, different from TRIGRS, presents results that vary from unconditionally stable to unconditionally unstable. So it's a different idea that has a limit value, a critical value. In this paper, the idea was to consider, in order to compare the 4 lower classes and the 4 upper classes, the 3 upper classes. So this is an issue about comparing models that present the results in a different way. But in some, both models perform similarly. When you verify the number of cells inside of the landslide scars. What brings us a question that TRIGRS is a more detailed model. You can add more input values than SHALSTAB. SHALSTAB is, using the words of the authors, as a more simple model. So a more refined model compared to a more simple model gives somehow similar results. So going to the end, you can see here these 2 charts that compare the landslide potential of the 6 scenarios for each model. And our results present that both models shows to be effective in predicting shallow landslides to comparison of areas predicted to be unstable and locations mapped landslides considering the 2 parameters. So you can see here the values are quite similar, especially look at the scenario A1. You have a lot of the landslide potential presents somehow similar results. Difference in model performance between scenarios A and B to the difference of effective cohesion and soil thickness values can help evaluate appropriate values of geotechnical data to incorporate into regional susceptibility maps. This is one of the things that a lot of people talk about, which value to use as input data for models. Of course, nobody has all the values for every square meter in the terrain. So we are evaluating different papers and try to understand where the values are, in how similar they are in order to create these scenarios. But of course, would be a very great help if you could improve the understanding about the variation of some values in the terrain. Let's like the cohesion or the dynamic of the water in the soil. This could help understand better the spatial influence of these parameters in landslide susceptibility mapping. As I said before finishing here, there are 2 main issues we are discussing now. There are 2 data that we can add to the models, the digital elevation model and the landslide scar model. So what's the best digital elevation model to use in some sort of models? And how big should be my landslide scar in order to evaluate scenarios? Let's say if you map the landslide scar in the rupture zone, the transport zone, and the deposit zone, your landslide scar will be very big. And the model will try to show where the rupture may occur. So depending how you map this, may give you a different results, not because the model is wrong, but because your approach about the validation method may not be suitable for some kind of test. And this brings us to another question: which resolution of DEM is best? Like, should we use a 90 meters DEM resolution, a spatial resolution raster, in order to map susceptibility in small watersheds? So there's some issues about the use of these models and the digital elevation models that we decided to apply in the test. As I said before, the equation of the models will not change it. We can just choose these 2 data, the landslide scar mapping and the DEM, and check the implications of this input data we decide to test to use in order to test our scenarios. So guys, I hope I made myself understandable. My English is quite rusty. And again, I want to thank you all, especially Roberto, for this invitation. And here's my email. I'd be glad to answer any questions. Feel free to contact me. Roberto, thank you. This is the finish of my presentation.